Hi guys, welcome back. So in the previous video, I introduced the way of actually doing the partial fractions for a fraction or for a rational function where the denominator was an irreducible quadratic form, and of course the degree of the numerator was still greater than the degree of the denominator, and then we had distinct factors in the denominator. But guys, here let's see if we can use that and apply it to this particular problem. Now, in order to evaluate this integral, again, I keep saying this all over and over again, guys. First of all, we have to see if there are other easier or simpler ways of evaluating this integral. Again, in this case, if you verify and test, you will not find. And guys, in case you find another way of doing it using an easier method, please feel free to share it with me as well, because we're all kind of learning things, and there's so many things that I may not know, or there's things that you may know I don't know, or things I know and you may not know. So let us try to create this culture of sharing things and educating each other. Okay, that being said, guys, I feel like we cannot use other simpler methods to actually simplify or integrate this rational function. So I'm going to try to use the idea of, or the concept of, partial fractions. So first of all, we can quickly see that the degree of the numerator is less than the degree of the denominator. Well, that qualifies for all the three types, type 1, type 2, type 3. But then let us look at the denominator carefully. And just looking at the denominator, if you haven't already watching or doing these types of examples, you know it is all about trying to factor the denominator. So without any delays, let's go ahead and do that. So this is going to be, I'm not going to worry about the integral right now. I'm only taking the integrand, which is inside this integral, and the factors. Let's see, we can already see the factors. The greatest common factor is x, and then we can see that what is left inside is the x squared plus 1. Now from here, I can see there's an x, which is a linear factor, and then I have a quadratic form, and I already know that I cannot write the factors for this quadratic form. So it means I have a linear factor, and then I have an irreducible quadratic form. So it kind of qualifies for both type 1 and type 2. So we have to use a combination of type 1 and type 2 to write the partial fractions for this particular rational function. So let us go ahead and do that. It's not too difficult. Guys, this is going to be equal to a divided by x, because the x is just a linear factor, so we got to use the type 1. Then to handle this guy, guys, I have to write not just a constant upstairs, we have to write a linear form, and I'm going to write the linear form like this, bx plus c. Guys, feel free to use a1, a2, b2, a3, whatever you like to use for constants. It does not really matter, as long as, you have to understand those are like constants, and we have to evaluate or find the values for those. Okay, I'm going to use b and c, and then I have to divide this by just x squared plus 1. That is the first basic step of breaking this into two pieces. And now here, because we still have two pieces and we still broke it into two partial fractions, but one has to figure out not just two constants, one has to figure out three constants in here. Okay, that is something special or different for type 3, where we have an irreducible quadratic form in the denominator compared to the other ones. Okay, this being said, guys, now we know from here the next step is to kind of get rid of this denominator, and that can easily be accomplished by multiplying both sides by this exact same term. So if I multiply left hand side by that, then let's see what this implies, that this will cross out. I will only be left with x plus 2 on the left hand side. On the right hand side, I have two terms, so I have to multiply by each individual term. When I multiply by the first ratio, the x's will cross out. I will be left with a times x squared plus 1. And then if I multiply to the second term, then x squared plus 1 and x squared plus 1 will cross out, and then I'll be left with only x. So I can write this as bx plus c times x, right? So the denominators are gone. Now from here, our goal is to try to solve for or find the values for a, b, and c. Right away, guys, I can see that if I set this x equal to 0, this whole term will just go away, but this won't go away, so I'll be able to find the value for a. So let us go ahead and do that. So I'm going to say let x equals to 0, and we are allowed to use any value for x, right? Any real value for x. Let x equal to 0. This goes away. This on the left hand side, I have 2 plus 0, which is just 2. On the right hand side, 0 squared is 0. 0 plus 1 is just 1. So it is a times 1. A times 1, guys, is simply a, and this we don't have to worry about it because this is already 0. I already have my value for a. A is positive 2, right? So guys, that takes care of the A. Now I have to try to find the values for B and C. So in this case, again, we may have to do some extra work in order to evaluate the value for B and for B as well as for C. So let us look at the equation. So guys, we should look at this, focus our attention to this particular equation. And from this equation, we have to see how one can evaluate the value for the B and C. Okay, so I'm going to show you one of the ways. Probably there's more ways of doing it. Guys, I already have the value for the A, right? Now I can, one of the things we can do here is we can substitute the value for X equals to, well, 0 will get rid of this. But I cannot come up with a real value for X here so that this whole term just vanishes, right? Because it's X squared plus 1. So we don't have any real solution for X here so that this becomes a 0. Of course, we have complex solutions, but this is all in the real number system, okay? So we have to figure out something else. What we can do is we can just use some other value for, how about we use any other convenient value or simpler value for X. So how about if I use let X equal to, how about 1? Let us see what happens if I use 1. Again, I chose 1 just for convenience. It's simpler, it's a smaller number, and it's easy to work with that number. So if I let X equal to 1, let's see what happens. 1 plus 2 is 3. So I will have a 3 on the left hand side. So I'm going to write that 3. Then on the right hand side, it's A times this whole thing. But A, guys, is already 2. So I can replace A with 2. And then what is inside the parentheses? X squared plus 1, but X is 1, right? X is 1, I hope you can see that 1. 1 squared is 1, 1 plus 1 is 2, so it is 2 times 2, right? And then plus, let us see what we can do here. Guys, this is B, we don't know the value for B. B times 1 is just B, and then B plus C times 1. Well, times 1 is not going to change this quantity, it's still B plus C. Let us try to simplify. Guys, 2 times 2 is 4. So let me take it up right here. I have 3 equals to 2 times 2 is 4 plus B plus C, right? From this, I can solve for B plus C by subtracting 4 from both sides. So I will have B plus C is -1, right? Guys, I cannot eliminate this A, right? So that is why we have to choose any other convenient value or simpler value for X, substitute back, and then try to see what we have on the right hand side and on the left hand side. Here we are able to actually get an equation, but we have both B and C. From this equation, still we cannot evaluate or calculate B or C. So what we can do here is, we can choose another value for X, and then from there we may be able to get another equation in terms of B and C. Then we'll have 2 simultaneous linear equations. And guys, we know how to solve 2 simultaneous linear equations. So let us try and choose any other simpler value for X. How about, again, guys, you are free to choose any other values, any values for X for that matter. But guys, I'm going to keep choosing like smaller values. So how about, I already did 0 here, so this crossed away. Then I did X equals to 1. Again, it was pretty easy to work with that. How about if I use X equal to -1, okay? So if I set X equal to -1, and then let me write it out here. Let X equal to -1. So if I let X equal to -1, then let us see what is how we can use that and what it simplifies to. So it's -1 plus 2 is +1 equals to, I already have the value for A, which is 2. I got to put that 2. Then inside the parentheses, I have to do -1 squared plus 1. -1 squared is still going to be +1. +1 plus 1 is +2. It is still 2. It did not change because of that square thing. And then let us see what is going on with the other term, guys. Then there's a plus B times, it's in the parentheses. Parentheses B times -1. So how about B times -1 is just -B plus C. Then I still have to multiply that parentheses by a -1. Okay, we can still do it. It's not too difficult to work with that. So this is going to be 1 equals to, this 1 equals to 2 times 2 is 4. And then we are going to distribute that -1 with these two terms. So when I distribute this -1, it will become +B and minus c. Why? Because negative 1 times this negative b will become positive b. Negative 1 times positive c is going to become negative c. From this equation right here, I can solve for b minus c just by subtracting 4 from both sides. So I will get b minus c equals to negative 3. Here I have another linear equation which relates b and c. Then I already had one more. I have two simultaneous system of equations, and from these two equations we can easily solve for b as well as c, and that's our goal, to solve for a, b and c. Once we have those, then we can try to find the integral. So guys, I'm going to make some more room, and then we are going to try to simplify this and find the integral. Guys, I know these problems are like longer problems, and I highly appreciate your patience watching these videos and like taking notes and making points and understanding these concepts. So keep doing it, and then keep practicing these problems on your own as well. So let us take this up and simplify. So what do I have? I have b plus c. How about, wait a minute guys, I'm gonna get rid of this 2 and bring it, do it on the side. So I already have b minus c equals to, so get rid of this, and then I'm going to bring this together. B minus c, I already have this equation, then I'm going to write this other one. And usually that's what we do with the simultaneous equations. We like to write them one about the other so that we can easily see which method is going to work for us to solve this equation. So you can easily see that, I mean, you can use substitution if you like, but elimination is going to be quicker here. We can add both these equations. So if I add both these equations, b plus b, of course we add vertically, b plus b is 2b. Positive c and minus c is just going to cross out. And when I add the right hand side, they will add up to negative 4. From here I get b equals to negative 2. Once I have b equal to negative 2, then I can either go back to this equation or the other one to find the value for c. How about if I use this equation to find the value for c? So I have negative 2 plus c equals to negative 1. To find c, I simply have to add 2 to both sides. So I'm going to add 2 to both sides here as well. So this crosses out. I have c equals to positive 1. A is known, b is known, and c is also known, right? Well, what was the value for a? Let me see. Okay, we had a equals to 2. So I'm going to bring this all together. So guys, this is equal to integral of 2 over x dx, and then plus integral of, guys, a is 2, we already calculated that, and then this was bx plus c. Ba is negative 2x plus c. What is my c? C is positive 1 over x squared plus 1, and then this in parentheses, and then I have a dx. So let us rewrite this again so that we can clearly see this. So it is going to be integral of 2 over x dx. How about this? Plus, I'm going to break this into 2 pieces. This is going to be integral of negative 2x over x squared plus 1. And the reason why I'm breaking this into 2 pieces, one, I'm mathematically allowed to do that. Number 2, the reason is that just by looking at this guy right here, we may not be able to evaluate the integral of this whole rational function. So if we break it into 2 pieces, then we may be able to see the functions where we can actually evaluate the integral, whether by using some other methods, which we will see once we actually break it into these 2 pieces, or by using some sort of direct formulas. So this is going to be my second term, and then the third, because I'm breaking it, it's going to be 1 over x squared plus 1 dx. Okay guys, I did not do anything crazy. These were 2 terms, so I just broke them into 2 pieces because this term as well as this term is both has to be divided by x squared plus 1. So now let us look at each individual term and see if we can write the integral. Guys, the first one is a simple one. You can take out the 2. Then integral of an inverse function of the form 1 over x is just simply, we already know that is just a standard basic formula, the ln of x. So that takes care of this. Guys, here we don't have any direct formulas for this, but just this x squared plus 1 in the denominator already tells me or gives me a hint that the substitution method should actually work for something like this. So let us take up the substitution method on the side and see if using the substitution method. It's simple substitution method if we can actually evaluate this integral. So on the side here, let us try and see if we can use the substitution method. So this is an example where we are using a lot of things. So, and that was one of the reasons why I chose this example, because it gives me an opportunity to share with you so many different things or different concepts in just one particular example. So we already have learned about the substitution method. So guys, this is a very simple example for the substitution method. So what we are going to do here is for evaluating this, so I'm doing this on the side. So integration of negative 2x over x squared plus 1 dx. Guys, I'm going to say use the substitution, let u equals to, of course, obviously I'm going to use the x squared plus 1 because we use the more complex piece, or what the piece or the quantity that has an exponent. So x squared plus 1 is an obvious choice. Then you know the second step is to take the derivative with respect to x in this case, because it's with respect to x, so it is 2x, right? And then you solve for dx, which is going to be du over 2x. I'm going to circle these two, you bring these in step 3, you bring these together and substitute back. So it's going to look like this: integral of negative 2x, we don't do anything with that, x squared plus 1 is just simply u, then dx is, guys, du over 2x. And then from here, you know, we expect and hope that the x's will cross out and we'll only have it in just one variable. So in this case, again, the 2x crosses out, it's just negative 1 over u du. I already took that outside. And what is the integral of 1 over u? It's again an inverse function. So we know the integral of this is just simply negative ln of u. Guys, but the original form is in terms of the x. So the final answer also has to be in terms of x. Now we already know what is u, and we go back to step number 1. So final value for the integral of this middle piece here is going to be negative ln, and then u is x squared plus 1. Okay, guys, we had to go on the side to do that. If I had space, I would actually keep doing it right here. It's up to you how you want to do it, but I'm just going to bring it back here. So it is just minus ln of x squared plus 1. That is the second one. And now we have to look at the third one. So guys, for the third one, you can just look at the quick like formulas on in your formula sheets or in your calculus textbook. Or guys, I personally am not such a big fan of remembering everything. Yes, you have to remember some formulas, but for me, I like to kind of discover things based on like my understanding of different types and concepts and examples. So for me to do something like this, let's say I don't have a formula sheet and I forgot what I can do, then what comes to my mind is like this qualifies for something which we have talked about, which is the trig functions or trig techniques of simplifying integrals. So this x squared plus 1, or I think of that as 1 plus x squared in the denominator. So that 1 plus x squared kind of reminds me of 1 plus tangent squared theta identity. So based on that, again, we're trying to go back and do the substitution, but in this case we call it a trig substitution. Okay, guys, again, those things come with experience and practice. If you are wondering how did I know like to think about the tangent function and not just think about any other substitution or any other function, guys, those things come with practice. If you keep on practicing these examples, you will also get to like know what to use, where to use. Okay, so I'm going to show you on the side. If you are allowed to use a formula sheet, you can actually look at the formula sheet and just write this in one step. But let us, for a second, let us assume we don't have that formula sheet, or we want to see how to actually evaluate this integral. To evaluate this integral, we are going to do, I'm going to say let x equal to tangent of theta. Guys, again, substitution is a very important method of evaluating integrals. So here you can see that we are using a partial fraction decomposition method, but then again, we still have to use the substitution method, and we also have to use the trig substitution method. So they are kind of all interconnected. So one has to know all of these things. X equals to tangent of theta. So I'm just trying to evaluate this guy. Then the second step for the substitution, which is like a general step for every type of substitution, is to take the derivative of the function. In this case, it's dx over d theta. And the derivative of the tangent theta is just the secant squared theta, okay? And then from here, we solve for dx. Very easy, just cross multiply, secant squared theta, d theta. That is the dx. This is my x equal to tan theta. I substitute back. Let us see what I get. I get 1 over tan squared theta plus 1 in the denominator, and dx is secant square theta d theta. Good. So guys, from here, this is just simply secant square theta, but tan square theta plus 1 is a trig identity, a Pythagorean trig identity, which is equivalent to secant square theta. So that, and there was a reason why I actually chose this substitution, and then times d theta. The good news is that this will cross out, so you're only left with just 1 d theta, and if I have to take the integral of 1 with respect to d theta, we know it is just the constant 1 times the theta, which is just the theta by itself. So the integral of this function is theta, which is in terms of theta, but the original function is in terms of x. So the final answer also is supposed to be in terms of x, but that is not too difficult to get it back in terms of x, because guys, let us go back to this step number 1, the substitution step. X equals to tangent theta. So from this, you can easily solve for theta by applying or taking the inverse on both sides, because we just want the theta by itself. So to get the theta, we have to apply the inverse of the tangent. So theta is just the tangent inverse of x. So the final integral, or the final value for the integral of this is tangent inverse x. Guys, you can also see that directly from a formula, but I wanted to show you like how you can use substitution and the right trig substitution to actually evaluate that integral. Don't forget to put a plus c. Here we have the integral of this function. Yes, we had to go through so many things, so many hoops to actually finally get it. But guys, this is the type of problems that we see when we are trying to evaluate the integral. There's so many different types. Type 3, guys, I showed you this example based on the type 3 general formula, especially irreducible quadratic form. Okay, so guys, I will see you next time. Till then, keep practicing. If you have any questions, any comments, feel free to reach out to me through my YouTube channel. Okay.